Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit, where we're going to be talking about total probability. Now, this is a little bit of an extension of a topic we talked about in a previous Thursday Tidbit, which I will link below, and that was the idea of conditional probability. So you're still trying to find the probability of A, but now maybe you know B happens, right? So the key word here is this given B. Now, you don't always need a formula for this, but we'll see a lot of examples today where directly or indirectly this formula is useful. And so the idea then is the probability of A given B is now the universe where B is happening. So we have the probability of B in our denominator, and then our numerator is the probability of A intersect B. So it's the probability of A and B both happening divided by the probability that actually B happens, because that is the given in this scenario. Right now we can rewrite this, and a lot of times actually this rewriting of the formula is almost as important or more important than the original form. This is actually the version of conditional probability we're going to use a lot today. So here, just multiplying both sides by P of B, we of course have that the probability of A intersect B is the probability of B times the probability of A given B in this scenario. So we'll see some examples of this. This rule is sometimes called the product rule or something like that. But right, these conditional probability things are useful and do come up in a lot of kind of real world scenarios as well. Let's look at a few simple examples that all kind of have this same setup. So real simple, we have 6 cards numbered 1 through 6. You're randomly dealt a first card and then a second card, right? So just to be clear, you have both cards there, right? First and second, you can't get the same card twice or anything like that there. So first question, fairly simple. If you look at the first card and see it is odd, what is the probability the second card is odd? This is one of those examples that the conditional probability is simple, right? We have 6 cards, but we're dealt a first card, so we only have 5 cards left. We have 3 even, 3 odd, right? 1, 3, 5 are even, 2, 4, 6 are, 1, 3, 5 are odd, 2, 4, 6 are even, right? If we see the first card is odd, we have 2 odds left, 3 evens left, 5 cards, 2/5 chance that we have an odd card for our second card in this scenario. That did not use the conditional probability formula, right? Just after we look at that first card, there are 5 left. 2 of those cards left are odd in this case. Okay, so let's take it a step further here, right? So what is the probability that the first and second cards are both odd? Now you probably could answer this without even thinking about it, right? So the first card, 3/6 chance that it is an odd number. And then as we just saw, we can multiply this by a 2/5 chance that the second card is also odd. All right, so we're just kind of doing this one step at a time. And so we end up with a 1/5 chance that both cards are odd in this case. So we just took it one step at a time, right? First card and then second card. If you think about this, we were really using the conditional probability product rule from before. This is the probability that the first card is odd times the probability that the second card is odd given that the first card is odd in this case there. So this isn't anything to do with quite total probability yet, but let's look at same setup now, a little bit different, and we want to give ourselves a little bit of more room in this case too. So our question, same setup, 6 cards, 1 through 6. What is the probability that the second card is odd in this case? Now, right off the bat, you probably can come up with an intuitive answer in this scenario. Right? Intuitively, the answer here should just be 3/6, right? Or a half in this case. Why is that? Well, we have 6 cards, 3 of them are odd, right? So why does it matter that it's the second card or things like that there? So this is correct, but I want to introduce this idea of total probability and kind of introduce a slightly more formal way of coming up with this 1/2 answer we have there as well. Right, and what's a little bit confusing about this is you might kind of ask the question, how can we know about the second card without knowing about the first card? Well, why don't we think about that then? And this is exactly what the law of total probability does. So we can think about cases here. And I'm going to kind of draw these cases in a tree to kind of help organize things and help organize our thought processes and calculations there. Right, so it really kind of depends on the first card. Right, so the first card has 2 possibilities. Right, when we start thinking about this, the first card could be odd. So we have a first card could be odd, or the first card could be even in this case. And so then, right, based on those 2 cases, we can do stuff for the second probability, the second card being odd in this case. Right, so if the first card is odd, right, we have then a what chance that the second card is also odd? Well, this is the one we kind of already started doing, right? This is just going to be a, well, there are 2 odd cards left out of the 5 cards left there. If the first is even, we still have 5 cards left, except now all 3 of the odds cards are left, and so we have a 3/5 chance in this case. Now, the mistake sometimes people make is, okay, these are the 2 cases, we add these probabilities together, things like that. But don't forget that the first being odd and the first being even have their kind of respective chances as well. Right? There's a 3/6 or 1/2 chance that the first card is odd. There is a 1/2 chance also that the first card is even. So actually, right, if we want to kind of look at where this 1/2 comes from in a little bit more detail, we can say there's a 1/2 chance that the first card is odd. Given that, there is a 2/5 chance that the second card is odd in that case. The other case is that the first card is even. And then we have a 3/5 chance in that case that the second card is odd. So we have 1/2 times 2/5, that's 2/10. 1/2 times 3/5, that's 5/10. And we shouldn't be too surprised, right, that this does match our same answer as before. We have a probability of 1/2 in this case. Now, I'll see a formula. We'll do a little bit more of a complicated example in a second too, but you really want to kind of think about this as cases, right? We have one case where we have the first being odd and then a probability there. So we have our 1/2 times 2/5, and then, right, that is one portion of our answer there. And the other portion of our answer in this case then is the first being even, and then given that, what happens from there. So we have a 1/2 times 3/5 in that case, and so we add up those 2 cases together. That is the total probability. So total probability, really want to think about this in terms of cases there. Okay. So writing this out a little bit more formally and in some of our symbols and stuff like that, right? The law of total probability for this scenario where we have 2 cases, right? So just to be kind of clear again about what these cases mean. In this case, we have B and B complement. So remember, the B complement just kind of means the opposite of B. So we have one scenario where B happens and the other scenario that B does not happen. And then given that, right, we can say, okay, if B happens, what's the probability of A happening in this case? So that is our A given B there. And then we have what is the probability of B happening in the second case? So here we have probability of A given B complement there. And as I mentioned, don't forget that kind of when you're doing these cases, you have to take into account those probabilities. So just to kind of make it more of a formula tree here, right? We have those same two kind of situations as before. You have the probability of B happening, and then the probability of A given B in that case. So that is one case that could happen for A. And our other scenario is B does not happen. So what is the probability that B does not happen? And then what is the probability of A given B in that case there? So that is our second half of this expression here as well. Now, you don't always need to do this, right? It's very important that we use this when the A given B or A given B is easier to calculate than A directly, right? And so a good example to think about that is like the previous problem, right? You need to know, or you might think you need to know if you're not doing it intuitively, what the first card is before you can say how many cards are left or dealing with the second card. So that's really this law of total probability here. We're not going to write it out formally, but hopefully this kind of makes it clear, and thinking about the tree diagram helps with this. This will work with 3 cases or 4 cases or however many cases you have. So let's end with an example where we have 3 cases in this scenario. Now, this is a little bit complicated to say. Well, we'll say it on this slide, then we'll do the calculation on the next one. It's really not so bad, though, right? So we start by flipping a fair coin twice. We're playing this game. It's actually going to be a pretty easy game, we'll see. Spoilers for the answer on the next slide. You flip the coin twice. So then, based on the number of heads, right, you could get 0 heads, 1 head, or 2 heads. You roll the die 0, 1, or 2 times. You win the game unless you roll a 1, right? So you want to not roll a 1 all of the time there. You might be asking, and we will see this on the next slide, this does mean you automatically win if you get 0 heads, right? Because if you get 0 heads, you do not even roll the die at all. And so you do not roll a 1, right? So that will be considered a win in this case. Right? Now, hopefully we can kind of see that this is a good situation where the law of total probability should be applied. We don't know how many times we roll the die unless we know the number of heads we got, right? So we have to do some cases here based on, right, the number of heads we could get in this scenario. And so if we're kind of actually going to calculate this probability, let's start looking at this then here, where we have a little bit more room to draw our picture again. So we have our tree scenario one more time. And remember, we can do this based on the cases of the number of heads, right? So one case we have is 0 heads, right? Then we have a 1 heads case, and we have a 2 heads case here as well, right? So labeling these, right, this is a 0 heads case. We have 1 heads here as well. And then we have 2 heads as our kind of final scenario in that case there. Now, don't forget that we want to associate probabilities with these things, right? 0 heads means both of our flips are tails, tails, tails. So that is a 1/4 chance in that case. If we get 1 heads, we get 1 heads, 1 tails, or 1 tails, 1 heads. So this is a 1/2 chance in that case. And 2 heads is also a 1/4 chance there. All right, so these are the probabilities that we go down these 3 cases there. They add up to 1, which they should, right? Something should happen. One of our 3 cases should be going on in this case. Now, what is the probability we win in these scenarios, right? So let's kind of maybe write it out here in this case. So the probability we win, given that we have 0 heads, right? Well, that is going to be automatic. So remember here, if we don't roll the dice at all, 0 heads, 0 dice rolls, meaning that we automatically do not roll a 1. Right? If we roll the dice once, right? So if we have win given kind of 1 head here, that should just be a 5/6 chance, right? You have 5 numbers that are not a 1 and only 1 1. So you have a 5/6 chance of winning there. And in our third scenario, right, we have a win given 2 heads. This one's a little bit harder, but we have 5/6 times 5/6. So this is 5/6 squared. So that quantity squared, both times we roll, we can't get a 1. So this has a probability of 25/36 in this case there. Now, how do we put this all together, right? How do we put this into our total probability formula? Well, just think of it intuitively again. We go down the first branch, so we have a 1/4 chance of going down this branch, and then the probability we win in that case is 1. So if we start collecting our final answer here on the bottom, right, there's a 1/4 chance we have 0 heads, and we have a 100% chance of winning in that scenario. Next scenario, we get 1 heads. So we go down this middle branch, there's a 1/2 chance we go down this branch. The probability we win in this case is 5/6. So here then, if we go down this branch, we have a 1/2 chance. Then given that 1/2 chance, we have a 5/6 chance of winning. And I'll highlight it after the fact, right? But we have the same thing for the third branch there. All right, so we have 1/4 times 36 in our denominator and 25 in our numerator. So we have 1/4 times 25/36 in this third case there. So that is our third branch. We go down, we have our 1/4 shot, and then the probability we win in that case is 25/36. So adding these all together, right, just a little bit of arithmetic here, you will get 121/144. So can't really simplify our solution at all in this case. But summary, the probability we win, like I said, it's actually a pretty easy game. You should expect to win almost all of the time in this scenario. We have a 121/144 chance that we're winning there. So again, just more cases, you have more branches of the tree, but the idea and the process isn't really any different there in this case. That'll do it then for this video. Check back each Thursday for a new math tidbit in 2021. We have a lot of great resources on the ZIML site too, Zoom International Math League, so I hope you guys check that out as well. And lastly, if you like this, right, please subscribe, please give it a like, that really helps out, and I will see everybody next week. Goodbye.